AP Calculus AB, Unit 7, Day 7, review, extra credit review for your test. Some more good practice. You have to analyze functions from their graphs. Zeros are going to be at x equals zeros, or where the function equals 0, not the derivative. So that's going to be A, C, E, and I. They're x-intercepts. Inflection points, concave down, concave down, concave up, concave down, are going to happen when concavity changes. Does it change at D? Could change at a cusp, but it doesn't. So let's say F and G are the only inflection points on this graph. Stationary points are where F prime equals 0. That's like critical points, but only the smooth ones. So B, F, and H. B, F, and H. Intervals of increase, that's where F prime is positive. The graph is going up, so that would be A to B. We include the endpoints. Then be D to E to F to G to H. Do not split it up. D to H, include the endpoints. Because we include the endpoints, that's why we don't spread. Increase of F prime, that'd be F double prime is positive, where we're looking for concave up. So that'd be F to G, but we don't usually include endpoints for concavity, but it didn't ask for concavity, it asked for something being increasing. So we are going to include the endpoints. Relative extrema, so we have relative maxes at x equals B and H, and we have a relative min at x equals D. So high and low points. Absolute extrema, the absolute max is at x equals H, and the absolute min is at x equals D. So those can happen at peaks and valleys, but sometimes they happen at the endpoints. So you want to make sure you check the endpoints. Intervals where F is increasing and concave down at the same time. Increasing positive derivative, concave down, second derivative. So where is it going up, but concave down? So I'd say A to B. Do we include the endpoints for A? No, because the end of concavity. Do we include the endpoints for B? Yes, because it's in the middle of concave down, and it's the edge of increasing, which we include for increasing. I would also say D to F is concave down, and would not include D because it's the edge of concavity, and I wouldn't include F because it's the edge of concavity. And then we also have G to H. I would not include it for G because it's at the edge of concavity. I would include H because it's in the middle of concave down and it's the edge of increasing. So we would include that. Bunch of points right there. Quick, not a lot of work. Make sure you get them right though. This is the graph of the derivative. So I go through and say, all right, positive increasing, negative decreasing, positive increasing, positive increasing. Then I go, all right, critical point, critical point, critical point. And then I say, okay, well, it's going up and down. So that's a relative max. Down and up, that's a relative min. That one's neither. Then I look at the second derivative of concavity. It's concave down, slope of the slope. This is a graph of slope values already. So the slopes of this graph are the second derivative. Concave down. F double prime is positive, concave up. F double prime is negative, concave down. F double prime is positive, concave up. So we have inflection points where it changes concavity. So I think we have everything we need to answer all the questions they could throw at us. Relative max is at x equals 1. Inflection points are at x equals 2, 4, and 5. F is decreasing from 1 to 3, and we include the endpoints. F is concave up from 2 to 4. We do not include the endpoints. And also 5 to 6, we do not include the endpoints. Can we sketch the original graph from this derivative graph? A lot of times we do a plus C over here, but we know that it's 2. So what I would do is I break it down, and really all we're going to do is make a rough graph. Is it going up or down? Is it concave up or down? So this first chunk is going up but it's concave down. You usually just do like almost like quarter circles. It should be smooth. Next one is going down and concave down. Okay, if the original graph is smooth, this graph should be smooth. Then it's going down, but concave up. And then it's going up and concave up. And then it's going up and concave down. And then it's going up and concave up. So something like this. And this should actually match all the answers you just got. Okay, what if I just give you derivative all done, all factored, all nicely in one fraction? Could you crank it out? Hopefully. Set equals 0 undefined. You should write that down. So we have x equals 3. We have x equals negative 4, which is a bounce. And we have e the x equals 3, so x equals natural log of 3. Now, e is about 2.8 or 2.7, so this is about 1. It's a little bigger than 1. A little bigger than 1. We do a line check. We're going to label it. If we don't, I'm taking off points. Let me put these points left to right. Negative 4, 0, 3. Don't forget that it's a bounce. Oh, and don't forget natural log of 3, which should be like right here. Test a value. X equals 4. Positive, positive, positive. It's all positive, negative, positive, negative, negative. Missing the bounces screws everything up. So it's decreasing. Did I make a mistake? I think I'm good. Oh, I put 0 in there as if it were a critical point. It's not. Positive, negative, positive, positive. Don't add extra ones. Okay. So these are actually increasing, increasing, and then decreasing, and then increasing. This is a relative min. This is a relative max. My graph is a horrible mess now. If I had a pencil, I'd erase and probably start. Okay, so we have relative max at x equals the natural log of 3, and we have relative min at x equals 3. There you go. Keep going. Okay, functions with rational exponents are always a little extra challenging. Always check out the domain. Any domain issues with this guy? Any negative exponents? Nope. Any even denominators, which would be even root? Nope. So I think we're good right now. Domains all reals. Might want to write that down. Okay. Below the x-axis. Now, I don't really usually ask that question. It's not very interesting, but you'd be doing a line check with the original function, so you would have to factor the original function, and you get x to the 3/3 minus 10. Factor out the smallest exponent, so it equals 0 undefined. That's a 1, so x equals 0, but it's a multiple root because of the even numerator, and x equals 10. So your line check would look like this. Test the value. X equals 11, positive, negative, negative. Now this is below. This isn't slope. This is below, above the x-axis. So we said below the x-axis. So I think we're going to say it's below the x-axis from negative infinity to 0. Union 0 to 10. You got to break it up. Don't include if it's on the x-axis. It's not below the x-axis. So increasing, we got to find the derivative. So I'm going to take the derivative of the original one. It's going to be 5/3 x to the 2/3 minus 20/3 x to the negative 1/3 equals 0 undefined. Now I'm going to factor these out. So I'm going to factor a 5/3 out and an x to the negative 1/3, smallest exponent. I get x to the positive 3/3, because rules of exponents, minus 4 equals 0 undefined. So x equals 4, x equals 0 is a critical point. I'm going to do a line check, label it 0, 4, test a point, x equals 5, everything's positive, negative, positive, so increasing, decreasing, increasing, increasing, decreasing, increasing. This work also tells you the relative mins and relative maxes. A lot of good stuff. So increasing is just going to be this guy and this guy. So we're going to say negative infinity to 0, and we include the endpoints, and 4 to positive infinity. Include the endpoints. We never include infinity. The only reason you might not include an endpoint is if there was a domain issue that you would, of course, need to consider. Concave down, got to find the second derivative. So that's going to be 10/9 x to the negative 1/3 plus 20/9 x to the negative 4/3. We're going to factor it, the 10/9 out and the x to the negative 4/3, smallest exponent. You're going to get positive x to the 3/3 plus 2, which is 1. We're going to set it equals 0 undefined. That should be in your work. So we get x equals 0, which is a bounce because of its even exponent, and x equals negative 2. That's an inflection point. That one's for sure not. I know that just because if it bounces, then it's not going to change sign. But it should still end up on your graph. Let's make sure I didn't make a mistake, because I feel like I made a mistake. Or maybe my solution's at a mistake. Ooh. My solutions might have a mistake. Yeah. Did they? F prime. Double. Oh no, we're good. Okay, we're good. Test a value. X equals 1. Everything is positive, positive, negative, concave down, concave up, concave up. So there's an inflection point right here. So it's concave down from negative infinity to negative 2. Do not include endpoints. If I was looking for a concave up, I'd have to split it up. Negative 2 to 0, 0 to infinity, parentheses. Now, could we make a quick sketch using all this information? Probably. I don't know. Let's see. I'm not going to ask you to do this on the test, but it's just good practice. So I start with the zeros at 0 and 10. Right? And then you also know this guy is bounce, and you know that it's below here, here, and above here. And then you know it's increasing. Now we get a relative min at 4, so it's going to be a low point. And then this is a relative max, that's a high point. And then concavity changes at negative 2 and 0. So I think the graph is, well, the derivative is actually undefined at 0, so it's like a cusp. So it's concave down, up to, it's concave down, then it's concave up, and then it's still concave up, and it goes through here. It's concave up all the rest of the way. So something like that seems pretty good. Matches all the information in the picture. Okay, got a couple more. When is this function increasing? So we want to take the derivative. It's going to be 2 cosine 2x plus 1 equals 0 undefined. So we got a little trig problem due. Cosine 2x equals negative 1/2. Alpha equals pi over 3. Quadrants 2 and quadrants 3. 2x equals, quadrant 2 would be 2 pi over 3 plus 2 pi k. And then 2x would equal 4 pi over 3 plus 2 pi k. And we divide by 2, divide by 2, divide by 2, divide by 2. X equals pi over 3 plus pi k. x equals 2 pi over 3 plus pi k. So x equals pi over 3, 2 pi over 3, and that's all we care about right now. That's your critical point. So we're going to do a line check f prime of x, pi over 3, 2 pi over 3. Put your limits on there, 0 and pi, your endpoints. Test a point. I like test 0. 0, and the derivative is positive, negative, positive, increasing, decreasing, increasing. And we're looking for increasing, right? So this is increasing. So we're going to say the answer is negative infinity to, or actually not negative infinity, 0 to pi over 3, brackets, and 2 pi over 3 to pi. So remember the endpoints. They affect your answer. Now, this is applying to the same problem. Find all the values of C is guaranteed by the mean value theorem. Okay, so that's one of those new things. So we got to find the average derivative first using mean value theorem. So we're going to have to do f of pi minus f of 0 over pi minus 0. And f of pi is going to be pi, and 0 is going to be 0. So we can get pi over pi, which is 1. So that's f prime average. So then we need to find the derivative just using our rules. So it's going to be 2 cosine 2x plus 1, and we need to set it equal to 1. So that's going to be 2 cosine 2x equals 0, cosine 2x equals 0, 2x equals, cosine equals 0, pi over 2 plus pi k, half the period, divide by 2, x equals pi over 4 plus pi over 2k. We want all the values between 0 and pi. So those are, we call those C values, by the way, now. This is the location where the actual derivative equals the average derivative, which is guaranteed to happen at least once if the requirements for a mean value theorem are met at the beginning. Okay, concave down. So domain needs to be positive. X equals plus or minus I root 2, but that doesn't mean we still do a line check, test the value like x equals 0, and if it's positive, it's true. It's true everywhere. It's all reals. Okay? I need to see evidence that you thought about it. Because just because it didn't matter this time, next time it probably will. So we got to find the first derivative, 1 over what's inside times the derivative of what's inside, chain rule. And we're going to concavity, so we don't need to do anything else here. Keep moving to second derivative. Low d high minus high d low all over low squared. So it's 2x squared plus 4 minus 4x squared, which is negative 2x squared plus 4 over x squared plus 2 squared, which is negative 2x squared minus 2 over x squared plus 2 squared. And we set this equal to 0 undefined. It's going off my paper here. Okay, now on the bottom, we get x equals plus or minus 2i. All right, we're going to throw those out. The top, we're going to get x equals plus or minus the root of 2. Those are good. These are inflection points. So a line check, negative root 2, positive root 2, test the value. Maybe 0 would be nice. 0 is going to be positive. Negative, negative, concave down, concave up, concave down. These are inflection points. So it is concave down from negative infinity to negative root 2. Do not include the endpoints. And positive root 2 to positive infinity do not include the endpoints. All right. Number 8, find the exact value and nature of the relative extreme of this graph. So we got to take the first derivative. We got to do product roll x times e to the negative 2x times derivative of what's inside is negative 2 plus e to the negative 2x times derivative of x is 1. You set that equal to 0 undefined. You clean it up. Negative 2x e to the negative 2x plus e to the negative 2x equals 0 undefined. I would factor this, kind of like what we did with the rational exponent problems. I would take a e to the negative 2x out. Now, undefined potentially comes from the denominator, but this guy is never going to be 0. This comes from that. So x equals positive 1/2. That's your critical point. We're going to do a line check. 1/2 test x equals 1. Or should we do 0? I don't know. If you plug 1 in here, I think it's going to be negative. Negative, positive, increasing, decreasing, relative max. So we have relative max at x equals 1/2 and a relative min at nowhere. Now here's an interesting question. If I asked you for the absolute max, or absolute extreme for this, you could tell me in this very special case that this is an absolute max. Even though we don't have endpoints, we can't do EVT, that would also be the absolute max. That would be, now it says find the exact value in nature of the relative extrema. So I made a little mistake. They usually ask me for the x coordinate, but they said the actual relative extrema. We need the y values. So we got to plug 1/2 in back in the original function. So f of 1/2 is 1/2 e to the negative 2 times 1/2 is going to be 1/2e. So the relative max is 1/2e. Relative max is 1/2e at x equals 1/2. That's also the absolute maximum. Okay. Optimization. Rectangular area, 3,200 feet squared, is to be fenced off. Two opposite sides cost $10 a foot. Remaining sides will be using fencing. It's $20 a foot. Draw a picture. I want to make the thicker stuff the more expensive stuff. That's up to you. I don't care. Okay, I'm going to call these X. I'm going to call these Y. You can use whatever letters you want. You use the same letters in different spots. So the area is going to be XY, but we want it in terms of one variable, right? Or actually, we're not even trying to do cost. The cost is going to be 20x plus 20x plus 10y plus 10y. And so the cost equals 40x plus 20y. We want to get this in one variable. We have the constant area of 3,200, which comes from x times y. So now we can say y equals 3,200 over x. So now our cost function could be 40x plus 20 times 3,200 over x. So the cost function is 40x plus 64,000 over x. Okay. You gotta take the derivative, c prime. It's gonna be 40. I would rather treat this as 64,000 x to the negative 1, so it could just be negative 64,000 x to the negative 2. I'm gonna rewrite it. 40 minus 64,000 over x squared equals 0 undefined. I'm not going to cross multiply because I'm going to lose critical points if I do that. So I need to combine these guys in the same fraction, least common denominator. So we have 40x squared minus 64,000 all over x squared equals 0 undefined. So undefined comes from the bottom. X equals 0 is a bounce. This guy on the top, it's going to be x squared equals 64,000 divided by 40 This should be 16. So we have x squared equals 1600. Square root of both sides. Plus or minus. You better have plus or minus. Plus or minus. Is it 40? So those are critical points. Now we need endpoints. Could x be 0? No, we don't have endpoints. Because if x goes 0, you don't have 3,200 square feet anymore. And then x goes to infinity. As y gets really tiny, x gets really big to make up for it, to have the constant slope. So we can't do extreme value theorem. We can kind of analyze it with a table, but it's still hard to back it up. So this is your cost function, 40x plus 20 times 3,200 over x. We could say the limit as x goes to 0, and positive 40 isn't going to get used. We say the limit as x goes to positive infinity. So as x goes 0, that goes 0, but that blows up. It blows up. As x goes to infinity, that goes 0, but that blows up. It blows up. If you plug 40 in, you get 1600 plus 20 over 3200 over 40 would give you 80, would give you 1600, would give you 3200. This is clearly the min because the graph blows up the other places. But justifying that when I require justification is a bit harder. So we could try to use first derivative test, which is also hard to defend, but it's another option. So we have c prime, negative 40, positive 40, test a point, maybe x equals 0 into the derivative. No, can't do 0. 0, by the way, is on here. So we can't test 0. Could I test like 1 or something? That would be negative. This is a balance. Negative, positive, positive. So it's increasing, decreasing, decreasing, increasing, increasing, decreasing, decreasing, increasing. It's a relative max. It's a relative min. On its own, you can't determine that, but we know that x has to be bigger than 0. So we're really focusing on that. Throw that away. I probably have that in my work still. And now, if this is the only place we're allowed to look, this is going to be an absolute min. Now, justifying it, is a little hard. And we could say the least cost is $3,200 when the $20 per foot sides are, that's what x was from here, right? Are 40 feet. And the $10 per foot sides are, now I think it's right here, 80 feet. That's the answer. To justify it, you got to use first derivative test to justify the ultimate. You could say since there is a relative minimum by the first derivative test, for relative extrema, you got to explain how it works. Since c prime is negative on the interval 0 to 40, and c prime is positive on the interval 40 to positive infinity. So that justifies the relative min. And then you got to say, well, because it's the only relative extrema, it must also be an absolute min. I'm not going to write that, but you can write that. It's the same thing I've written before. Now, this problem is just kind of crazy hard. It's good practice, I guess. And I'm cool with using a calculator on the table. to get some decimals to make sure that you know which one's max min, or you could use first derivative test. Not really sure that's that much easier. New track will feature a perimeter that's 4 meters, like a traditional track, and unique shape consisting of semicircle, rectangle, and equilateral triangle is shown. Find the radius of the semicircle, maximizing the total area enclosed. Hint: area of equilateral triangle is square root of 3 over 4 sides, side squared. So we're trying to find radius to maximize total area. So we've got to get an area formula. So we have R, we have X. So this is going to be 1/2 pi R squared. This is going to be 2RX, because, right, 2RX. And the sides of the triangle, it's going to be 1/2 base times height in general, but this is a equilateral triangle, so 60, 60, 60. I mean, even if I didn't give you that formula, you guys should be able to maybe recreate it. 30, 30. The height, so 30, 60, 90 triangle. So if this is 2R, right, then this is R, and this is R root 3. So even without that formula, I think you guys can find the area. It's going to be 1/2. The base is going to be 2R. The height is going to be R root 3. You get the same thing as if you just plug 2R into this. Plug 2R in here, you get 4R squared. You're going to get root 3. So, now I want it in one variable. That's where the 400, the perimeter of the shape comes in, which is 1/2 of 2 pi R circumference plus 2 x's plus these two sides here, which are another 4R. It should add 400. So we could either solve for x or r. I think it'd be easier to solve for x. So 2x equals 400 minus 4r minus pi r divided by 2. So that's your x. X equals 200 minus 2r minus 1/2 pi r. So then we can plug that in for the x's right here. So our area formula now is 1/2 pi r squared plus 2r times 200 minus 2r minus 1/2 pi r. Plus, this is going to be r squared root 3. This is ugly. This is ugly. Okay, let's clean it up a little bit. 1/2 pi r squared plus 400r minus 4r squared minus pi r squared plus r squared root 3. I think there's some like terms, like we can combine these guys together. Why not? Sure, why not? So that's going to be negative 1/2 pi r squared now. So no calculus yet, just lots of geometry, algebra. Okay, let's just make sure that all looks right. Okay. So now the calculus, take the derivative. That's going to be negative pi r plus 400 minus 8r plus 2 root 3r. I'm going to set equals 0 undefined. It's never going to be undefined this time. We need to solve for r. So I'm going to factor the r out. We have negative pi minus 8 plus 2 root 3. I'm going to move the 400 to the other side. I'm going to divide both sides by this. So r equals, I'm going to get rid of the negative. I'm going to factor negative out of the top and bottom. That'll make things a little nicer. This is your critical point. It's not super pretty, but what are the endpoints? Could r be 0 and the track still be 400 meters? Yes, it would just be a back and forth track. What's the biggest r can be? Well, the biggest r would be if x was 0, right? We just got rid of all that. We share all of the track on the triangle and the circle. So if x equals 0, we have this equation. then R, I can move these over here. Multiply the top and bottom by 2. So R equals 400 over 4 plus pi. That's your endpoint. That's your max R endpoint. Well, we found endpoints and critical points so far. They're slightly ugly. So now we're going to make a table with R plugged in. And these are going as the area formula, right? Okay, 0, 400 over 4 plus pi, and 400 over pi plus 8 minus 2 root 3. So we're going to plug each of those in. Actually, this goes here. You got the order wrong. That's the critical point. Plug 0 in. I think we pulled that one off pretty well. The area is 0. That's the back four shot. Okay. Plug this in. I'm not even going to write it down. Using my calculator, I got 10,420.071. Plugging this, actually, that's for this one because I messed up the order. This one ends up being 10,361.397. So we're looking for max area. It happens at the critical point. So the maximum area is 10,420.071 meters squared when R equals, because that's what they specifically asked for, 400 over pi plus 8 minus 2 root 3 meters by the extreme value theorem, thankfully. By checking endpoints and critical points. There you go. That's it. That was crazy. I'm not going to make you do something like that on test, but it's good practice.